Hello everyone and welcome to another Solve With Me video. Today we'll be talking about electromagnetic induction. So let's begin with the first question. A metal rod of length L is pulled upward with constant velocity v through a uniform magnetic field B that points out of the plane of the page. So it points out of the page. Since v is upward, so this one is v is upward and B is out of the page, as you can see. The direction of FB on the free electrons will be to the left, leaving an excess of positive charge at the right. Therefore, the potential at B will be higher than the potential at A. By this formula, we know that the answer is E, with point B at the higher potential. Alright, this is a formula that you pretty much have to know. All our trees to revise it right now. Okay, now let's go to the next exercise, which is 2. The circle and ellipse below have the same area. So A1 equals to A2. If the both loops are held so that their plane is perpendicular to a uniform magnetic field B, how would phi C, the magnetic flux through the circular loop, compare to phi E, the magnetic flux through the elliptical loop? So let's do this. If the plane of a loop enclosing an area A is perpendicular to a uniform magnetic field of strength B, then the magnetic flux of the loop is going to be equal to the product. So we know this formula, right? And this is because they are perpendicular and the angle is 90 degrees. Since both these loops have the same area, the magnetic fluxes through them will be the same regardless of their shape, because we know that. So the answer is C, right? Okay, now let's go to the third exercise. The figure below shows a small circular loop of wire in the plane of a long straight wire that carries a steady current I upward. If the loop is moved from distance x2 to distance x1 from the straight wire, what will be the direction of the induced current in the loop with the direction of the corresponding magnetic field it produces? So, to the right of the let's take a look here, okay? And they say that, okay, take a look at this diagram. And we know that, so to the right of the long straight wire, the magnetic field points into the plane of the page, and it is stronger at x1 than at x2, right? This means that the into the page magnetic flux through the loop increases as the loop is moved from x1 to x2. Since the flux is into the page and increasing, Lenz's law says that the current induced in the loop will be counterclockwise to produce its own out-of-the-page magnetic field. So, the answer to this question is C. The induced current will be counterclockwise and the magnetic field it produces will point out of the plane of the page. Now let's take a look at the next question. A square loop of wire, side length S, look at the diagram, surrounds a long straight wire such that the wire passes through the center of the square. Alright, so they ask, if the current in the wire is I, determine the current induced in the square loop. Okay. So, a change in the magnitude of a magnetic field requires either a change in the magnitude of the current, or a change in the area of a current coil. Since the current in the straight wire is steady, there is no change in the magnetic field, no change in magnetic flux, and therefore no induced EMF or current. So the answer to this question is E, 0, right? Okay, now let's go to the next question. In the figure below, permanent bar magnet is pulled upward with a constant velocity through a loop of wire. So take a look at this figure. Now, let's see. They ask us which of the following best describes the directions of the current induced in the loop looking down on the loop from above. So, by definition, magnetic field lines emerge from the North Pole and enter to the South Pole. So let's do some small lines here. From the North Pole to the South Pole, from the North Pole to the South, like this. And here also from the North to the South, right? And it's gonna be like this and like this. Okay, therefore, as the North Pole is moved upward through the loop, the upward magnetic flux increases. To oppose an increasing upward flux, the direction of the induced current will be clockwise, as seen from the above, to generate some downward magnetic flux. So let's take a look here. Okay? Now, as the south pole moves away from the center of the loop, there is a decreasing upward magnetic flux, so the direction of the induced current will be counterclockwise. So, the answer is C. First clockwise and then counterclockwise, or this is anti-clockwise, okay? This can also be understood like this. So this is for today. This was the electromagnetic induction.